Okay. Yep. So alrighty, let's go team. The 11th lecture. We're probably going to have maybe 3 more before the next exam. Exam 2, fun time next, number 2. Alright, so let's see. Okay, so a lot of things are going to start coming together. We're going to figure out this story here. I'm going to show you some stuff about movies. A little bit of fun, right? Okay. This is our happiness measuring thing. So today we're going to talk about spanning sets, bases, and dimensions. And we've touched on this. We've had a few spoilers about this, but it's going to start to tie things together. Some of the ambiguity, as I'm sure in your minds, will hopefully start to kind of evaporate. We're going to play with this little matrix here. You can give it your own personal name. This is the star of the day. We will come back to our friend here because it's a good, healthy example. And how M and N, right? M and N, you've got them straight away. Number of rows, number of columns. Boom, boom, straight away. Are the number of pivot columns. How they tell you everything you want to know about, well, the really big story about null space and column space. And I'll repeat again and again what that means for solving AX equals B. This scintillating thing that you guys are working on. All right. All right, so let's play around. Let's see what's on the web here. Let's push the right buttons. Maybe. Right, all your bases belong to us. Actually, so it's, right, okay. Team members. So we're going to be talking about a basis for a vector space or a subspace, and the plural of that is bases, not bases. But anyway, all right, so there's some other good stuff. Little bits of wisdom here, truths apparently. I can delete them if they're not. But you should look at the tweets. Look at the tweets. Okay, so here's a little bit of fun. So we have about 1,000, you can play around with this. This is on hedonometer.org, we've just put this up. So it's the bottom project here, 1,000 movie scripts. So the thing about movie scripts is that there's direction in them, right? So it's not just what people say or the characters say, there's the actions, right? So you can go through and harvest and look at the words in the description as well. So we have this crazy little business, I think I showed you some for books, where we run a little window through the script and measure the happiness according to our algorithm. And so you can do this. You can wander through the script like this, and the script will pan down on the right there. Right, so this is The Princess Bride. I'm sure you are all fans of The Princess Bride. This is when Christopher Guest gets it, right? My name is Inigo Montoya. People with 6 fingers, you should be very careful. So that's that little low point because lots of fighting and it's getting pretty serious. So you can annotate this actually. So if, again, with this Twitter business, you can log in and you can annotate. It'll give you all these little places where the highs and lows are. So it's kind of a group effort thing. So there are 1,000 in there. There's his Pulp Fiction knowledge. So the lowest point here is the GIMP section, which is pretty terrifying. I mean, I found that, anyway. It's in the eye of the beholder, of course, but that was a kind of a rough scene. So, as I said, it's not just, the GIMP doesn't say much, for example, but there's what the GIMP does is describe. Lots of good things in here. Star Wars, ridiculous, right? So this is Luke walking the plank. Tragically, he lives. Everything is it. Finding Nemo, Despicable Me 2 is in here. It's a bit of a Godfather, so it's a bit of a diverse range. Anyway, the idea is hopefully if you play around with this, you can read it, right? So you can pop out here and read the script. Let me find, and you can search. Okay, so, thank you. So Predator. Predator just goes bad, right? There's all the buddies are here. We're going to have some fun hunting, and then it's not good. It's just not good. There's no up. A lot of them have ups and downs, emotional. They're yanking your chain the whole way. This is a lot of stories are structured like this. There's a nadir towards the end to kind of, and then it ends well. But this is pretty bad. And as I think I was saying this before, these scripts you can't get the originals, you can't get the real scripts, right? It's copyright. So this is an earlier version. That's what we have. This is Hunter. They changed the name. They kind of improved the name there a little bit. But there are so there's Alien v Predator in here. You know, there's it really is Godfather. So it's the full gamut of movies in terms of quality and kind. Anyway, so what does random is fun? The Flintstones, right? That's intent. That's good because that started. Right? This one? Oh, it's not going to do it. I can't go backwards. Coraline. Oh, Highlander. Yes. Yes. The best, worst movie from the 80s. Okay, all right. There can be only one. The Shining. Yeah. Let's, yeah. Yeah. Okay, so that's some good stuff. City of Joy. Crying Game. That's intense. So there's a lot of good stuff in there. So you can annotate these things. Get in there and play around with it. Well, that's a bit obscure. Stephen King fans, it's good. The Saint, Val Kilmer? No? Val Kilmer fans? No. It's fine. Another 80s character. All right, so there's some fun for you. But you really you can play around with this. So let's talk about linear algebra. All right. All right. Okay. So this is where we're going today, bases and so on. We're going to see this character come back, this matrix. We've explored it. We know something about it. It's a little bit of a mess, and we're going to look at this. This little character here is pretty useful. All right. What else? Okay. Say things. All right, people, off we go. So, this is actually a section for fans of the book. This is where we are in the book. Probably edition 3 or 4, they're pretty much the same. Okay, so as I said, we've got today bases and spanning sets and dimensions of subspaces. So, we're going to explore the joys of this particular matrix, AX equals B, when A equals this simple little character here, 2, 2, 4, 1, 2. If you want to call it, give it a name, Cecil, something like that, if that helps. That's all right. It's okay to name your matrices. No one's going to, well, all right. Okay, so let's do our things. Okay, so first, we're going to find column space and null space. Let's do it. Space, and that is C of A, and the null space of A. We're going to use this one method we have so far. We have one method, we'll introduce another method today, right? There's going to be 3 ways of doing this. 3 ways of doing. We only have one. There's one spectacular way of doing this. All right, so we solve A, B. Same story. You've learned. So the tools. This is a good thing about this, at least, apart from its inherently interesting nature, is that the things we've developed along row reduction, all these things. You just keep using them, right? I'm not going to pull it away and say no, that's no good. By row reduction for general B. This is for general B. This is the idea. Once again, to say what we're doing. So this is going to be 1, 2, 2, 4, 1, 2, B1, B2. Right? What we're asking here is which B's can A's columns make? Right? Linear combinations of A's columns. And because we're just saying B1 and B2, let's see if we can make any B1, B2, or maybe there's a constraint. And you probably, if you've looked at this a little bit, as we throw these things on the board, you can see something pretty straightforward about it. So we always do the same procedure, right? So row 2 prime equals row 2 minus. The monks have led us in the right direction. We're not going into a hedge maze. Okay. If they lead you into a hedge maze, that is bad. Okay, so this is going to be 2 divided by 1. Okay. Right? Right? Okay. You can write down the next step. What do you get over here? Row 1 does not change. So implicitly, there's always row 1 prime equals row 1. That's always, right? That's always just hanging around there. Okay, write down the next row. Yes. Pretty good, right? So this row is a multiple of the first one, so it all disappears. 0, 0, 0. So it's an interesting kind of thing, and we have B2 minus 2B1. All right, so when we go back out to equations, now there's always a point where we step, well, let's do this properly. Row reduction, we are done. We are done. There's a 1 here, so we don't even have to divide by the pivot. First pivot equals 1, which we call D1, which is crazy. But anyway, so this is the pivot column. This is a pivot column. Say these things again, pivot column. So one thing we'll repeat over and over and over again is express the pivots in terms of the free variables, right? That is a thing you must remember over and over again. And we'll see why the monks told us to do that. I know the monks are there, they talk to me. Okay, so pivot column, free column. Free columns. There are 2 free columns. So this is, it looks a bit funny, right? We don't have, it's not as big as the other guest star that we'll have later on. But that's it. There's nothing more we can do with this. We can't get rid of this number or this number. These are free. And we've got our reduced row echelon form. There's a little step there. Okay, so we're done. And so for C of A, we must have a solution, right? It must be solvable, right? So A, very simple, AX equals B must be solvable. And the problem lines, right? Problematic rows are those with zeros in R sub A. I've been naughty. Let me write this as well. So this is equal to, this whole thing is equal to R sub A D. So many things will be revealed. It's great. 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 Right? So it's the row 2 is row 2. Row 2 gives us 0 times x1 plus 0 times x2 plus 0 times x3. I'm repeating these things because it's good to do. B2 minus 2b1. 0 equals b2 minus 2b1. Right? 0 has to equal 0. Row 2, 1 is a problem. So we have this constraint. b2 equals 2b1. Or, of course, we could say b1 equals a half b2. So let me just pursue a little bit with this ambiguity here, because this is a slight disappointment. So there's some ambiguity with our method here, with CA finding, with this first method for finding, this is just something we're living with, for finding C of A. Why do we do it if there's ambiguity? That's not what the monks want, right? But this is a good intuitive story. You want AX equals B to have a solution. You find the conditions on B for which that is true. So C of A then. It's always going to be this kind of thing. We say B equals B1, B2 equals, right? Always do this. Always. If you're having, you can be cavalier and go crazy. That's fine. You can just write down the column space, but, at your own peril. Okay, and then we'll have to replace one here. So we can say B1 and B2 is 2B1. Right? So we replace B2. And this kind of stuff always happens. There's a B1 here. There's just it's not to be confused with free variables, but there's no constraint on the B1. Or we could do this. B equals B1 B2, right? I'm going to put in always. That applies this way too. We're going to do this. We'll replace the B1 with a half B2. Half B2, B2, which equals B2 times a half 1. And very important thing to add, always, B1 is an element of the real numbers. B2 is an element of the real numbers. There's no constraint on B2. There's no constraint on B1. Are these the same thing? They are, right? So you'll always get the same thing. It's not, this is just a one-dimensional thing, so it's pretty clear. It's easy to see. So we can see we have two descriptions, so this is very important, two descriptions of the same thing. Right? Someone describes a camel to you and they just change the order of the words around. Not a salad, the phrases say, right? And then, but they're equivalent. Of the same subspace of R2. Right? So this guy looks like, let's draw it, so the C of A, and it lives in, this is always a little confusing, we're going to do it again and again, Y1, Y2 for column space, so it's 1 and then 2, right? So here's 1 and 2, and this is a half and 1, so we could have had that one, a half and 1, and so any multiple, this is column space. And writing it as a set, which is the really, now this is the very grown-up thing to do, we can say it's y equal to, in this case, I'll use that one, this is B1, 1, 2, B1 is an element of the real numbers. This is a line in R2. Passes through the origin, here's our origin, little thing on it. So A will take any, what does A do? A is, forgot to write this down. This is 2 by 3, right? So this is M equals 2, N equals 3. A sends 3-dimensional vectors, you can think of it like that, to 2 dimensions. So if you think about that as well, it's taking a 3-dimensional vector and sending it to 2 dimensions. Taking something in all of space, what we think of as space, and sending it onto a plane. So something has to be lost, right? It's squishing a whole bunch of stuff. So it's kind of clear that you can't go backwards from that. That's something we'll get to, right? There's no way you can undo that. All right, that's an extra piece. All right, that's column space, and we've noted 2 ways to describe it. But, you know, we need to overcome that, right? We don't want to say, all right, there will be better ways to describe these subspaces. Right, so we're getting to that. Piece of paper. Okay. That's column space. And let's go back to the matrix. It's clear. Look at the columns. 1, 2, 2, 4, 1, 2. So we went through all this little bit of machinery. It's any multiple of 1, 2 plus any multiple of 2, 4 plus any multiple of 1, 2. These guys are the same. This one is twice this one. You can see it, right? That's all this matrix can do, because if you multiply this by x, you're just saying x1 times this guy plus x2 times this guy plus x3 times this guy. That's all you can do, right? Right. Should I write that? Oh, okay. So it's obvious from, the worst word ever, obvious from A. Because we can say A times x equals x1, 1, 2, plus x2 times 2, 4 plus x3. This is exciting, people. I'm psyched. x1 plus 2x2 plus x3. This is what our matrix Cecil does. Okay, I call it Cecil. So you can throw any numbers in here, right? It doesn't matter, x1, x2, x3. This is just some scalar. Has to be a multiple of 1, 2. It's manifest in A times x. Okay. All right, null space of A. Grooviness. Okay. Null space of A. Right, so this is when does AX equals 0, the so-called homogeneous equation. or because we like it so much, or the null space equation, which will appear in an unusual kind of way. Well, it'll pop out again in a different setting soon. All right. So good. Okay, good. We've done our hard work. We've done our row reduction. Where is it? Boom, it's here. Very simple. 1, 2, 1, 0, 0, 0. Now we're going to put zeros in here. It's a tiny example, so nothing crazy happens. We're going to put zeros in here. B equals 0. The initial B is 0. Then whatever you end up with, D is equal to 0 as well. Set B equal to 0 in this thing, D equals D, right? Okay, and so now we've got 1, 2, 1, 0, 0, 0, 0, 0. This is our problem. Null space, you get your reduced row echelon form. So it's R sub A 0. It's always this. Next. Always, always, always. So go back out to the x1 plus 2x2 plus x1 equals 0. That's the only equation we have. Right? Yes. x3. The universe continues. Thank you. All right. I've said this over and over again. Pivot in terms of the free. Right. Now, so this is an always. This means always. Express pivots in terms of the free. I'm writing funny things. Pivot variables in terms of free variables, depending on how many there are. This is a pivot. This is free. That guy, that's a free. That's a free. Okay, so it's x1 equals minus 2x2. There's a reason for this. Free. I'm going to write it again. I want to make it really clear. Free, pivot. That's a terrible F. Okay. I failed my F. Okay. These things can be any, so this is the sense why they're free, right? These things, we can let them be anything they want, and the pivot variable is tied. It's dependent. Okay. Where's my thing? Through blatant fear of losing things. I'm really good at losing things, actually. I think the best thing I ever did was lose my passport at the Melbourne Cricket Ground where there were 80,000 people. And I had to fly back to the US the next day. That was, and I didn't know I'd lost it there. That was bad. Okay. All right. Long story. And my mother did not have a heart attack, but that was probably a stress for her. Okay, so let's see. So sorry, Mum. I still feel bad about it. Okay. 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 All right. I wanted to put it on this board. Yes. Put it on this board. So nice. Look, it's a nice, comfy little equation. So we always do this. We always do this next step. Right? We're machines. Always do this. And I need a shorthand for this, ADT or something. So this should be x1, x2, x3. The pivot variable gets replaced by its expression in terms of the free. So replace pivot variable only. And so this equals, and what is it? It's minus 2x2 minus x3. And then these guys stay the same, x2, x3. Let's make something else in here to make it perhaps a little, if you're equals, if you're having a little trouble with these funny things. There's an x2 here, so that's 1 times x2. There's no x3, but we can write as plus x3. And then a 1x3, so we'll put that here, and then a 0 times x2 here. You can always do this, and then maybe it's easier to see the next step, which is there'll be x2, the free variable will be here. The next, every free variable will be here, free. Minus 2, 1, and 0. Minus 2, 1, 0, minus 1, 0, 1. Minus 1, 0, 1. So where x2, and x3 are elements of the real numbers. So this is the null space then. The null space of A, which kind of write out the whole thing again, it's a bit funny, is x equals x2 times minus 2, 1, 0, plus x3 times minus 1, 0, 1, where x2 and x3 are elements of the real numbers. And you can look at this, right? So A times, so a little bit of a check. Let's do this. 1, 2, 2, 4, 1, 2. I know we're doing these things again and again, but this little character, we're really going to dig deep with this one. So we're going to solve everything about it. Let's do that dot product, right? So dot product here, 1, 2, 1. So it's minus 2 plus 2, 0. So it's 0, 2, 4, 2. We get 0 as well, right? Etc. Right? This is A. Okay, so let's add some more words now. These are going to be called, so that's a little check. So we're going to call these the special solutions, which is pretty, not very special, but this is a special solution. Right? There's something special about these characters. Do I divert myself into this now? Maybe. Well, let's just notice some things. Okay, I'm not going to do it yet. All right. Okay. Good. Where am I? Okay, so what is this thing in 3 dimensions? It's in 3 dimensions. It is a plane. It's a plane in 3 dimensions, right? So it's any multiple of one vector plus any multiple of another vector. They're pointing something like this, and they take any combination of them, and you'll carve out a plane. So null space of A is a plane in R3, and this is 2D. This is n equals 3, and this is the plane here, right? Is 2D, is n minus r, and we're going to prove this today. So n minus r equals 3. What's the rank of this matrix? One. So the rank is 1. Damn it. Excellent. So rank is 1. R equals 1. Yay. Okay. All right. That's important. Thank you, Chair. Okay, so 3 minus 1 equals 2. Okay. I could work with a ladder, actually. You could have a whole, right, okay, let's see. So, all right, we've got that. We clean this up. This is going to go upstairs. So we're going to call these things special solutions. Let me just say something about it, though. Let's say, so we can, so here's a thing to do. So we'll put the special solutions together. So this is in general to form a matrix we'll call N. And so here's N for this one. It's minus 2, 1, 0, and minus 1, 0, and 1. Now, it's going to be a bit trickier in general, but here's the thing that we'll see this over and over again. The identity matrix appears in this blob. It may be spread out in different ways. Matrix appears. This is always true. Always true. There'll be some details about it. And let me show you some other funny things. So this is the number of free variables, right? So this is n minus r. This is yet to be proved. This is n minus r this way, n minus r this way, which is equal to 2. So it's a 2 by 2. This identity matrix is a 2 by 2. And this little blob here is, this little matrix here is an r by n minus r. So in this case, it's a 1 by 2. So I'm just going to connect it to something about the reduced, about A, actually. No, the reduced row echelon form. Okay. We observe RA has this form. This is funny. But it's not. It's because the monks did this. Okay, so this is RA equals 1, 2, 1, 0, 0, 0. Now, there is an identity matrix in here, and there's this matrix as well. So this matrix, we're going to call this matrix F. And it's always going to be an M by n minus R. Sorry, an R by n minus R, which in this case is 1 by 2. And this little blob here is an identity matrix. And in general, it's an R by R. So in this case, a 1 by 1. The identity matrix 1 by 1 identity matrix is just 1. So there's actually some structure there. And this thing on the bottom, you'll always get these things. This is a 0 matrix. I'm going to kind of write a 0 like that. And in general, this is a M minus R by N. All zeros. So we can come back to this. But what's happening is because we did this thing, we said express the pivots in terms of the free up here. Right? So you see we have 1, 2, 1 there. 1, 2, 1. So when we take the 2, 1 onto the other side, we just make them into negative numbers. Right? There's 1, 2, 1. The equation is x1 plus 2x2 plus x3. So when we put the free variables on the other side, we just change the signs. -2 and -1. And that's what's happening here. Here's the F, 2 and 1. We put on the other side, we end up with -2 and -1. So this little blob here is minus F, the matrix minus F. So this is the way it's usually stacked. So in general, we may have to shuffle, and let me put in brackets, may have to shuffle the x's. And I'll give you another example. We're going all the way with this. It's great. We have this kind of form. RA equals the identity matrix times, and then a minus F matrix, and then a 0 matrix. And they have these shapes. This is an R by R. I know this is getting abstract. I'm getting it. I'm going to write it down. And this is an R by n minus R. And this is an m minus R by n. And this n matrix, right? This is the special solutions matrix. Matrix always looks like minus F with the identity matrix on the bottom. And this guy in here is again, it's the same F, R by n minus R. And this is n minus R by n minus R. What have I done? This is a plus. Yep. Thank you. Okay. Swap chalk. That's clearly the problem. Okay, so and here's a block multiplication thing. And then we'll go back out. We'll bring in our special guest star, and then we'll go back to bases and things. Multiplication. RA times n, right? If we multiply these things together, it's a bit funny to look at, but you get this big block times this character, and then this big block times this character, and it's going to look like this. I times minus F, and then there'll be plus F times I. And on the bottom, we get the zeros of everything. We get another 0 matrix, and this 0 matrix will be, let me get the right size, it's going to be an m minus r times n. So this is a different one. This is m minus r times n in size, This is an R by, I got it right? Yeah. This is R by N, right? I know, this is a little abstract, but look at this. This is I times minus F plus F times I. Minus F plus F. So this whole thing is a giant zero matrix, zeros over zeros, and it's a M by N. This is showing that this particular method that we use, expressing the pivots in terms of the free, it can be abstracted in this way, we can see it in this abstract way, and that it always does the right thing. It creates vectors, right? The vectors that are lying in here, these guys are the null space vectors. Right. The last thing here, so the big deal is that these special solutions are linearly independent. And I am getting ahead of myself. Are linearly independent. I'm going to say it all, and then we'll come back to what that means properly. Linearly independent. There's no way you can make one of these guys out of the others, right? So there's no way one solution, one vector can be made out of the others. You need them all. That's okay. So let's see it for these guys. It's minus 2, 1, 0, minus 2, 1, 0, right? And 1, minus 1, 0, 1. Because of this structure here, there's no way I can multiply this guy to get a 1 here. There's no way I can multiply this guy to get a 1 here. The presence of the identity makes them linearly independent. Okay, all right. Okay, one more dosage of pain in this direction. So let's go back to A equals this one. I'll just write down what we have. 2, 2, 6, 4, 4, 12. It turned out that this was a pivot row, column. This is a free column. 3, 6, 12, 4, 10, 18. I know we went hard on this one. Free. When we solved this, we ended up with, I could write it down like this. The null space vectors we got out of this were minus 2, 1, 0, and 0. Let me not write that down first. Let me write down the reduced row echelon form. That's important. Right. 1, 0, 0, 2, 0, 0, 0, 1, 0, minus 1, 2, 0. So let's unpack this beast in the way we've been talking about it. Here's our F. So here's the identity matrix. 1, 0, 0, 1. This is the identity matrix. This is a case where M equals 3, N equals 4, and R equals 2. So we said in general that this is an R by R, and that's true. This is an R equals 2. This is a 2 by 2. We can take the F matrix is going to be this part. Take the free variables and stick them together. 2, 0, minus 1, and 2. This is our F equals this thing. And it's an N minus R times, so R times, R times N minus R, which in this case is a 2 by 2. Okay, I know, painful. Let's do it. Then we're going to ease up a little bit. We found the null space, the special solutions for this. So from before, we can put them together now, the null space guys. So there's minus 2, 1, 0, 0, and 1, 0, minus 2, and 1. Did I get that right? Yes. So these are free entries. This is the pivot one. This is the pivot one. let's look at this. So it has the right architecture. Here it is. Here's the identity matrix. 1, 0, 0, 1. This is the identity matrix. The identity matrix in n has this shape. N minus y times n minus r. Good. Is that true? N minus r times n minus r, which is, in this case, 4 minus 2, 4 minus 2, so it's 2 by 2. Good. And then here, take these pieces, the first and third rows out, we get minus 2, 1, and 0. If I get that right, minus 2. Yes? Oh, okay, right, yeah, so that's confusing, isn't it? The first column is the pivot. The third column is the pivot column. Free variables are the second and the fourth ones. So that's what you get it from A, right? It's here, here. You get it from here. So x1 and x3 are the pivot variables. This is because x1 and x3 are the pivot variables. Right, RA comes along and multiplies this matrix. This is a confusing piece, definitely. I know it's all confusing. These are x2 and x4 are the free variables. And this comes from, this is from RA. That knowledge comes from RA. So this is minus F. It's the what we expected. Here's F is 2 minus 1, 0, 2. Okay, so once again, because these vectors have an identity matrix inside them, there's no way we can make one of them out of the others. Right? We can't take some multiple of this guy, because it's got a 0 here, and make this 1. We just can't do it. And if there were 30 of them, there'd be an identity matrix inside it. 1, all zeros, 0, 1, all zeros. There's no way we can build those pieces. Okay, I'm going to come back to that later on. I'm just going to refer to that when we get to telling some extra stories about null space. But that's a okay, nasty part over. You'll have to come back and look at this one. Okay, good. Good. Okay, medicine. That was good medicine. All right, so let's go back to 1, 2, 1 and 2, 4, 2. All right, so back to 1, 2, 2, 4, 1, 2. A equals this guy. Let's sort this out properly. So in general, now we've really got to sort some things out. So what time is it? Okay, so the column space of A is a subspace of, that means is a subspace of, and the null space of A is a subspace of which ones? M for monkey, right? And N for nuclear option. Okay, how about that? All right, so that's generally true. Well, we have to prove this. We have to prove this. We've kind of got the idea that this is probably true, but we have to prove this. That's where they live. So let's take our NA. Yes. So this is 6. NA equals, so it was, we had these guys, right? We had multiples of these vectors. Minus 2, 1, 0, minus 2, 1, 0, and minus 1, 0, 1. These are our special solutions. So, do they form a subspace of this case of R3? So do these things, do these vectors form a subspace of R3. I mean, absolutely. Yes, there's no problem, right? So, you know, it's very simple. So the subspace, the property of subspace, property 1 was x, y elements of our subspace, then x plus y is in the subspace. So let's look at it. It's a little tedious, but let's look at it. So we have, say, x is equal to C1 times minus 2, 1, 0, plus C2 times minus 1, 0, 1, and then y equals C3 minus 2, 1, 0, plus C4 minus 1, 0, 1. Sure, we can just add these together, x plus y, and then you just group things together. C1 plus C3, this is so silly, minus 2, 1, 0, plus the C2 and C4 go together. C2 plus C4 times minus 1, 0, 1. Sure, still the same form, right? It's some number times minus 2, 1, 0, minus 1, 0, 1. Fine. So this is still in the null space of A. All right, the null space of A is any multiple of this character plus any multiple of this character. So that's good. So subspace property 2. If x is in the subspace, then C is in the subspace. C times x is in the subspace. Right, where C is an element of the real numbers. Sure, totally, yes, of course. So C times any multiple of these things, minus 2, 1, 0, let's say C1 plus C2 times minus 1, 0, 1, sure. It's very, very silly. It's C times C1 times minus 2, 1, 0. So it's some number times C minus 2, 1, 0 plus some number times minus 1, 0, 1. I always feel very silly when I'm doing this. Sure, fine. Is 0 in there? And then we'll stop doing this. Subspace 3, yes. 0 is in the null space. Sure, 0 times minus 2, 0, 1 plus 1, 0 plus 0 times minus 1, 0, 1. Sure. Sure. Okay. Sure. So it's totally a null space, a subspace. All of these things where we pop out with x is some multiple of one vector plus another vector and so on. Right. That's fine. Okay, now we have to think a little bit about whether we've got enough vectors or too many. So here, this is now the issue, right? If you want to describe a space, a subspace, how do you do that well? So the big issue, the big question is, how do we describe subspaces well? Well, or efficiently. Efficiently, right? What's a compact thing? Because if you think about these sets that we write down, there's an infinite number. We hand over a box that has an infinite number of points in it. It's much easier to say that R2 is any multiple of I hat and J hat, and you just hand over I hat and J hat. That's it. That's just two vectors. That's much more efficient. All right. So let's do some. We'll do some definitions, right? So in general, yeah, sets, and this is what we've just looked at, made up of all linear combinations. Linear combinations. That means you can multiply each vector by any number you want and add them together. Of a collection of vectors. Vectors is a subspace. Are subspaces, right? Sets made up of their subspaces. Exactly because of this reasoning here. Okay. Fine. That's totally great. But what we're going to say now, so here's a, right, so here we're going to say this thing next. So new thing, we say these two guys, minus 2, 1, 0 and minus 1, 0, 1, span the subspace that is, in this case, the null space, right? They span it. So this is this new word. That means I can just hand you those two vectors and then you can recreate the whole subspace. Right? I can hand you a violin and a cello and you can make the whole thing. I don't have to get you to play every note. All right. That is exciting, isn't it? All right. And of course, you've been doing this over and over again in calculus and other places where you have I hat, j hat, k hat, you know, radial coordinates, whatever it is. You just hand over two things. So we span the subspace. So n of a, we can say is this, it's every, again, x equals every multiple of, I guess it was x2 minus 2, 0, 1 plus x3 minus 1, 0, 1, where x2 and x3 are elements of real numbers. This is, in here we have infinitely many points. Or we can say NA is spanned by, this is enough to do it, just two vectors, minus 2, 0, 1, we'll put them in brackets like this, minus 1, 0, 1. Two vectors. Yes, please stop me from talking. Points. It could be a prescription from a doctor. Spanned, right? Spanned. So this is much more efficient. Infinitely many points, two vectors. This is much more compact. Very nice. Right? I'm sure you're thinking it's very nice. Okay. So other sets could span it. So here's our problem. And we saw this right at the start of the lecture where there were two ways to describe column space that kind of naturally came out. So here's the kind of the problem. The other sets span the null space of A. This is a problem and a catastrophe. Right, could be a good thing as well. So what else? We could have this. We could just take any multiple of these. 2, minus 2, 0, 1, 3, minus 1, 0, 1. That works. That works. We can try trickier things. We could add two of these together. That becomes a little less obvious. But this works too. Minus 2, 0, 1. 2 times minus 2, 0, 1. And minus 1, 0, 1. We'll get all of null space by a linear combination of these three vectors. But this one's, there's a redundancy here, right? So we've created a redundancy. What I was argued with all the F and I business is that this is going to be the most minimal description. We can't go down to one vector, right? We need both of these vectors, or possibly two other vectors, but these vectors have a shape to them that allow us to see, what am I writing on now? This one. I know I'm not taking photos. Okay. It's all right. Okay. Okay. All right, people. I know it's more painful than it needs to be. No, it's not. Suffering is good. Okay. All right. Okay. Other examples of spanning sets. This is number board 83. Okay, so other examples. Well, these two, 1, 0 and 0, 1. These two span R2. We like these characters, right? And in fact, we're actually defining everything based on them anyway. They span R2. So you can get every vector from these characters. So does this. We could have 1, 1, 1, 0, and 0, 1. These span R2. Clearly we have a redundancy, right? Which sometimes we'll want. We could have this. This is fine, right? Let's make it minus 1, 1. I'll put a 1 over root 2 out the front, just for fun. And a 1 over root 2, so they're length 1, unit vectors. This works too. Spans R2. All right, so let's call this example A, B, and C. Right, and so the observation is B contains it has a redundancy. Too many. Right, too many vectors. You'll see that in fact everything we've been doing is about this, yes? What have I done? Yeah. This is a 1, 0, correct? And this is yes. The universe continues, thank you. It's good I don't design nuclear reactors. Okay, so good. So is this point taken, right? There are too many in this one. So how do we figure that out? All right. Well, so we can take. So in this case, we can actually take any one of them away. It'll be okay. In this case, we can't take this one away. We've got 2 copies essentially of this one. So we could delete this one or this one, we'd be okay. We cannot take that one away. So we have to be a little careful. Okay. So let's say, the words here are, in words, we say A and C are examples, and these are the words of a linearly independent set of vectors. Set of vectors. And C and B is an example of a linearly dependent set. Learn how to write. Set of vectors. There are a couple of things we're going to do. We'll want to clean this up. We'll want to just pare it down. And then later on, actually, even when we've got a nice basis, that's the word we're going to use, when we have a linearly independent one, we may actually want to manipulate and choose a better one, right? So depending on what you're doing, this might be a good basis. This could be a good basis, right? So we'll have to that's a spectacular thing that will come. All right. So it's all going to connect back to things. So let's do it like this. So here's a definition. Let's mathematize this. A set of vectors. This is awesome. A set of vectors. A1, A2. Let's suspiciously have n of them. We'll have n of these. And these guys can all be m by 1 vectors. It's very suspicious. A set of vectors is linearly independent. Linearly independent. And the way to think about it is no way to make one of them out of the others. Right, so here we can clearly make this one is, right, 1, 1 is 1, 0 plus 0, 1. We can create it that way. Is linearly independent if, my gosh, if x1 times a1 plus x2 times a2, that's a number, plus xn times an, equals 0 is only solved, is only true if x1 equals x2 equals xn equals 0. So you have to switch them all off. Now it's a bit funny, we're stacking them on one side. So why? The reason is if not, right, then we'd have some xi not equal to 0. Right? We have some xi not equal to 0. And then we could move them around, right? So, and then we could express, we could rearrange this equation to express one of these vectors, one of the ai in terms of the others. Right, and the simple example from B, that's others B, we had back over here, we could just write 1, 1 equals 1, 0 plus 0, 1. So we can get rid of this character. Right, or we could say this one is equal to 1, 1 minus 0, 1. We can get rid of it. Right, and this is the same, this comes from solving the equation. Let's say that in this order, 1, 0, 1, 1, 0, 1, right? This will be 1 minus 1 times this guy, 1 times this guy, plus 1 times this guy equals 0. Right? We're solving this equation. We're finding some x's. This is x1, x2, x3 times a3 times a2 times a1. We're finding some non-zero values of x's for which we can combine them to get 0. So it's a sort of a stylized representation. So what is this equation? This equation looks like something we've been working on. It's a null space equation. Oh, yes. Yes. This is just a times x. This is just solving a times x equals 0. I know you're thrilled by that. There's nothing new you need to know. It's the same story again. Is there some way of combining these instruments to get no sound, right? And if there is, then we can get rid of one of those instruments. Yes. Boom. Okay. That's good. This is good. This is really good. So let's go over here and say the next thing. So, once again, the monks have led us in a good direction. We don't have to learn anything new. All right, we'll get a little further. Let's see how far we can get. So here's an important definition. We've had what a spanning set is. So a spanning set is called a basis, is a basis, right? A spanning set for subspace S. Space S is a basis for S if the vectors are linearly independent. And we now know how to find that, right? So it's easy when we have this little example here. You can see it, fine. If you have a million by a million matrix, who knows? Another thing we can say here, so or you'll see this, or a minimal spanning set. It's all you need to define the whole thing. maybe it's not as exciting as I think. All right. So this is a note. Bases is pronounced, well, by me, as base e's, right? Okay, bases. More than one basis. Okay, so the big deal. This is a big deal. Bases are not unique. Big deals. Bases are not unique. Right? Big deals. C is a basis, A is a basis. And then they both describe the same thing. Right? Take every combination of these two vectors, you get R2. Take every combination of these two vectors, you get R2. This is not a basis. It still describes the same thing, but it's not a basis. So they're not unique. And then 2, some bases are better than others. And I know all bases should get a medal, but that is not how it works. Math is cruel. Are better than others. I know. People like to say it's all truth and beauty, but it's really just truth, and that's it. Okay, so beauty is very optional. Okay. Okay. Good. Okay, that's great. So the dimension. So big deals. And here's our new thing. So we have a base. So once we have a basis, so then the dimension of a subspace is the number of vectors in its basis, a basis for it. Okay. That's what we're trying to get to. Wow. I talk too much. Okay. I'm erasing the wrong thing. Okay. All right. Sorry. Okay. So definition. The dimension of a subspace is equal to the number of basis vectors, of vectors in any basis. Dimension of a subspace S is equal to the number of vectors in any basis for S. Right, so the one that I just erased, the one that had, so we had the 3, this was no good, right? So 3 vectors, that's a spanning set for R2, it has 3 vectors. We understand what R2 is. There's too many things. We need only 2 for R2. So you'll have that kind of right feel. Okay. Now, this is important, so let's get back to, and I'll see how far we can get with this. So, back to our little champion, Cecil the matrix, back to 1, 2. This guy, the dimension of column space is equal to 1, right? Because column space was equal to, let me write it like this, column space is equal to any multiple of 1, 2, where B is an element of real numbers. You can start to see that there's one basis vector there. All right, it's a one-dimensional space. We still have to prove this properly. The dimension of the null space of A was equal to 2. The null space of A, again, was equal to this funny-looking thing, minus 2, 0, 1, no, 1, 0. X1, x2 times this thing, plus x3 times minus 1, 0, 1, x2, x3 are elements of real numbers. And we can see visually from this, so the basis for CA, 1, 2, we can choose that. We could choose 2, 4, anything. So one basis for this, one basis for NA is just these two characters, minus 2, 1, 0. minus 1, 0, 1, write them out 1,000,000 times, 2 of them, one of these. That's the dimension. Okay. So what I'm going to do is just write down this next step. So in general, the dimension of, I know I've written this down before, but all right, the dimension of column space is equal to R, which equals the rank, which equals the number of pivot columns. It's always true. Or the number of pivot variables, and the dimension of the null space of A is equal to n minus R, where, again, rank, like this here, right? And this is the number of columns. And this is actually, what's n minus R? R is the number of pivot columns, n is the total number of columns. What are the other columns? They are free columns. So it's equal to the number of free columns. Okay, so I'm just going to do the first one. So y. So the work we did earlier, the work from earlier, that showed where we painfully showed, you need payoff for this, where we showed the null space vectors are equal to minus f in the identity. And so this thing is yeah, it's n by n minus r. Right, that's the shape of it. Good. Which is right. So we showed that this always happens. We showed this. These are the special solutions in here. So the because expressing the pivot variables, this is the key thing, key variables in terms of the free variables always creates this. Always creates this kind of structure. Kind of structure, kind of n. The special solutions are linearly independent. Are linearly independent. And it's because of this thing here, the identity matrix. Are linearly independent. And therefore they form a basis. A basis for the null space of A. And there are n columns, right? N rows, n minus r of these. Right, they form a basis for it. There are n minus r of them. It's the number of free columns. So the dimension of null space is always equal to the number of free columns. It's a tougher thing to think about. Now, we will talk about why the column space has a dimension of r, and then we will get into 2 other magical subspaces. And then we'll be done with this, sort of. All right, lots of pain, but think about bases and subspaces. Thank you. All right.